Okay, so let's go ahead and get started. So, a few things of note before we actually get into the lesson. First of all, Dr. Kibler came out with a statement about the COVID epidemic yesterday. That is on the Solross website. Just go to solross.edu and then click on the COVID notice up at the top, the banner there. And he has a video that you can watch. It's his statement on what's going on. And I suggest that you watch that. Also, in the email that I sent out this morning with the link to our stream, I also included a link to little tutorial about how to use Smart Thinking. And Smart Thinking is a service that Solross has. We've had it for, I think, 2 years now. And what it is an online tutoring tool. So if you need any help with anything, you can always go to Smart Thinking and get a live tutor. It is basically the same as the tutoring center. I wish this train would stop. It's the same thing as the tutoring center that we have on campus, except that it is online, and the employees for Smart Thinking are not Solross students, they are employees for Smart Thinking. Okay, so let's go ahead and get into it. So like I said last time, we are going to be covering inequalities today. So last time we talked about equations, and we said that equations, we have expressions that are equal to each other, and so they're being compared, something like 2x, 2x minus 3 equals x plus 7, something like that. Okay, so again, what we have here is we have two expressions, one of them 2x minus 3, and the other one x plus 7. And the equal sign between them shows perfect balance. So when we go to tackle this and try to solve for x, excuse me, we are going to get an answer that gives us an exact value for x. It might be that x could be one thing, it might be that x could be two things. And as we saw with our identity and contradiction equations, x could be all real numbers or x could be no numbers. However, there is some exact value for x. It's going to be one of those three types of things. So just as a quick recap, let's go ahead and solve this. So first things first, I would want to get x by itself. For this one, I'm going to actually bring my x value, this one right here, to the other side. So subtract x from this side, and subtract x from this side as well. Of course, what that does for us is it cancels on this side, getting rid of that x here, and brings it over here to the other x value. So now we have x minus 3 equals 7. Try again with that 7. Okay. So now we just need to take the 3, the negative 3, and cancel it. And again, we need to do the same thing to the other side to keep the balance that this equal sign shows. And so that cancels, and we get x equals 10. So again, this is what we would call a conditional equation. X has some condition for making this original equation work. So as long as we plug in 10 for our x value here, this will be the same thing. We'll get something equal to the correct thing. It'll make sense, in other words. Okay, but again, that's what we were saying with equations, is equations have balance, and that's because of this equal sign right here. With inequalities, what we're doing is something slightly different. The actual process is going to be very much the same, but the answer that we get is going to be a little bit different. It's a different idea. So let's have something kind of simple. 2x is greater than 4. So the way you read these is if the large open mouth part of this inequality comes first, it's greater than. And we read it left to right, of course. And if we encounter the small tail of the inequality first, that's less than. So just keep that in mind. This one is greater than, this one is less than. So this is read 2x is 2x is greater than 4. And like I said, we solve these basically the same way. It's the same process, but the idea behind it is different. 2x in this case has more weight than 4. There's not balance here, there's weight. So again, 2x has more weight than 4. This has to be bigger than this side. So again, idea here is to get x by itself. So do the opposite. If we're multiplying 2 by x here, we're going to divide by it here to cancel it. But we have to take it to the other side still. So now, on this side, since that canceled, we just have x. This inequality drops down, just like before. And 4 divided by 2 is 2. Okay, so this is still a condition. The condition here is that x has to be greater than 2 in order for this original thing to make sense. And yeah, if we plugged in something that was not greater than 2, for instance, if we plugged in 1 for x, that would be 2 times 1. 2 times 1 is 2. Is 2 greater than 4? No. However, if we plug in something bigger than 2, say 6, so 2 times 6 for our x, that'd be 12. 12 is indeed greater than 4. So that works. However, I also want you to notice that we cannot plug in 2 itself. This says x must be greater than 2, not equal to 2, greater than 2. Because if we plugged in 2 into x, this would be 2 times 2 is 4. 4 greater than 4? No. 4 is not greater than 4. 4 is equal to 4. So we cannot actually use 2 as a solution. So this is where we have to start thinking about what does our solution actually look like here? What are we going to say our solution is? Well, it's actually a really good idea to graph our solutions when we do something like this. So I'm going to make a number line. And I'm going to say that here about in the middle is 0. Okay, and then over here are the negative numbers, and over here are the positive numbers. All right. So if we want to graph this on a number line, there's actually some particulars that go into this, some strategies for how to graph this that are very standard in math. So just follow along with me. First of all, we need to know where 2 is, because that's where our solution set is placed, is somewhere around 2. So positive 2 is about right here. Now this says x is greater than 2, not equal to, just that it's greater than. So to show that we are not actually equal to this point here, like we said, we can't actually have 2 for x. That wouldn't work. To show that, we are going to use an open circle right on 2. An open circle shows that we start at this point, but we don't actually include it. And then all these solutions for x are greater than 2. Well, that's going to be all the numbers that are bigger than 2. So that's going to make a line from this starting point. Let's make a better line than that. that goes into the numbers that are bigger than 2. Okay. So this is how you would see this on a graph. Now again, what this is showing us is that, yes, our solutions start at 2. It doesn't include 2, though, because we can't have 2 be one of our answers for x. It just doesn't make sense to say that. Again, if we plugged in 2 here, 2 times 2 is 4. 4 is greater than 4? That's not true. 4 is exactly equal to 4. So 2 can't be a solution. However, everything after 2 is perfectly fine. For instance, 2.0000000000001, yeah, that's fine. It is going to give us something bigger than 4 if we multiply by 2. So everything directly after this 2 is part of our solutions. In fact, there's another way to write this, and that is using something called interval notation. Interval notation basically takes this idea of the graph and kind of condenses it down into something that's easier to look at and just quickly look at and say, all right, I know what the solutions are. So here's how that works. Interval notation is based off the idea that when we have one of these solutions that we graph here, it's going to have a start point and an end point. We read the graph left to right. We get our start point, which here is at 2. And then we have our end point. Now, the end point for this one's a little strange. It's infinity. So again, it starts at 2. Then it goes into infinity. So for our interval, we need to state our start point and our end point. Well, again, our start point is 2. And our end point is infinity. Of course, that means that our numbers can keep going on and on and on and on and on. We could put 200 billion into here for x, and it would still be greater than 4. It doesn't matter what it is. We could go into infinity with those answers. Now, the other part of this is that we have to say whether or not we can be equal to these start points and end points. So again, we look at this one, our start point, 2. Can we be equal to it? No. Again, we can't have 2 for a solution because it doesn't make sense in our equation. So the way we show that is with a parenthesis. We put a parenthesis around that 2. That parenthesis shows us no, we cannot be equal to this number. It just starts here, but we don't actually include this number. Infinity. So can we actually reach infinity? Can we actually include infinity? No. We can only approach infinity. We can't actually have the value infinity. So since we're just approaching it, not actually getting to it, this also gets a parenthesis because we cannot actually be equal to infinity. You can never be equal to infinity with these. Okay? So to go back over this one example here, we started with 2x is greater than 4, solve it, and we get this solution here. This is called a set builder solution. So this solution shows us that x must be greater than 2 in order for this thing to work. It has to be greater than 2, not equal to it. So when we think about our solution, we can graph it on a number line like this and more easily understand what that solution looks like with the graph. But then we can also use interval notation to just quickly make a little note about what this graph says. And once you get some practice with these intervals, you can understand the solution set pretty quickly. That's why they're so nice. So I will allow for a little bit of time for questions here. So again, just type into the comment section, the chat section, whatever questions you may have. And I'll give us some time since, again, like the note says, there's up to a 40-second delay for me getting that question on my side. Okay, I don't see any questions, so I will keep going. So, let's try another one of these. So let's try same basic idea. 3x plus 4 is less than or equal to, that little line underneath the inequality means or equal to 7. Okay. So once again, same structure that we've been seeing through all of our examples. We have some expression with a relationship to another expression. The relationship here is that it must be less than or equal to 7. So we can solve this again by moving things until we get x by itself. So minus 4 to both sides. So that cancels there. 7 minus 4 is 3. So we now have 3x is less than or equal to 3. Then one more step to get to our solution. We need to divide the 3 off of here. Since the 3 is multiplying by x, we divide it off to do the opposite. That cancels, and we do the same thing to this side, which means that our solution here is that x must be less than or equal to 3. I'm sorry, 1. 3 divided by 3 is 1. Okay, so with our previous example, again, we said that here x had to be just greater than 2. Just greater than. We could not have 2 be a solution for x. Here, though, this now says that we can have something smaller than 1 or equal to 1. So let's try that out. Let's put in 1. 3 times 1 is 3. 3 plus 4 is 7. 7 is indeed less than or equal to 7. Makes sense. Let's put in something smaller than 1. I don't know. 1/3. So put 1/3 in there. 1/3 times 3 is 1. 1 plus 4 is 5. 5 is indeed less than or equal to 7. Makes sense. So let's try something that's outside of our solution set just to make sure it works. 2. 2 is not in this solution set. 2 is not smaller than or equal to 1. So 3 times 2 is 6. 6 plus 4 is 10. That's not going to be less than or equal to 7, so that does not work. So this makes sense. This is indeed our solution. Again, let's go ahead and look at this on a number line, though. Always helps to think about our solution sets on a number line. So like I said before, number line, these are the negative numbers. These are the positive numbers. And here in the middle, we have 0. So 1 is where our solution set is located. So that's about right there. And it says that x can be less than or equal to 1. Remember that when we were looking at this one, we didn't have that or equal to. It was just greater than. So we used an open circle. For this one, since we can be equal to, what we will use instead is a closed circle, a filled-in dot, solid dot. That, again, shows us that we can be equal to 1 here. 1 is where our solution set starts, and we can include 1. Okay. Now this says that x is less than or equal to 1, so less than means it's all the numbers that are smaller than 1. So our solution set will extend out over here and keep going on into not infinity, but negative infinity. That's a distinction I have to make. There's a difference between positive infinity, which is over on this side, and negative infinity, which is over on this side. So when we go to make our interval, again, we need a start point and an end point, and that's always read from left to right. So our start point here is at negative infinity. And it goes all the way to here and then stops at positive 1. Try that again. So, again, intervals, start point, negative infinity, end point, 1. Can we be equal to infinity? No, so we will use a parenthesis around this. Can we be equal to 1 in this case, though? Absolutely. So instead of using a parenthesis, we're actually going to use a bracket. And there is our interval notation. So when we are working with these in Hawks or on a quiz or something, I will probably expect you to be able to use interval notation. So solve one of these and then put your solution in interval notation. That's one of the reasons that I want you to be able to graph them, is because graphing them helps us see that interval better. It helps us build it. Also, graphing it just helps us understand what the solution actually looks like. So the theme that we're seeing here is that our solutions for these inequalities, we don't get a specific answer. We don't get 1 or 2 numbers. We get an entire range of numbers. So like this one is all the numbers from negative infinity to 1 would work for x here. Whereas with a regular conditional equation, we'd get something like x equals 3. And that's it. So keep that in mind. Inequalities will have a range of numbers that will fit for x, whereas equations just have some single value. Or well, I shouldn't say single. Some specific value, like 2, 3, something like that. Okay. Another thing I want to show you. For the most part, so far, we have seen these inequalities, and there's not really any difference to them in solving them. It's the same process that we would use for solving an equation. So you just get x by itself. There is one extra step with these, and that is due to the fact that, again, equations show balance, whereas inequalities show weight. I got a question here, so I'm going to take a pause. Now, does the 1 get a bracket because it is less than or equal to sign? Yes! Again, what we're saying here is that the answer is that x could be less than or equal to 1. So when we graph it, we have to put that solid dot here to show that we can be equal to it. Equal to this 1 right here. And the 1 gets that bracket because, again, we can be equal to it. That's what we're showing with the parenthesis in the bracket. Can we actually be equal to these numbers? The parenthesis shows that we cannot actually be equal to this number. The parenthesis shows that we cannot be equal to this number. The bracket shows that we can be equal to this number. So because 1 is included in our solution, we can plug in 1 here and get an answer that perfectly makes sense. Then yeah, it can be equal to. And so we have to use that bracket. So good. If you see this equal to line underneath your inequality, it means that you're probably going to have a bracket here. Now, the only reason that infinity doesn't have a bracket on it is because we cannot ever quite reach infinity. And we can come all the way up toward it, but we can't actually reach it. I hope that answers your question. Let me know if it does. If not, then keep on going with your questions. For now, though, I'm going to start a new example. Again, like I was saying, so far, these have been basically the exact same as the equations. We solved them the exact same way. This one's going to be slightly different. And again, it's because these don't show balance, they show weight. So, I'm going to have negative 2x plus 5 is greater than or equal to, let's say, 7. Okay, good. I'm glad I answered that for you. Okay, so again, we're going to start this one basically the same way. You know, we got to get x by itself. So we're going to get rid of this 5 by subtracting on both sides. Again, that cancels the 5 here, leaving us with a negative 2x. And on this side, 7 minus 5 is 2. So we now have greater than or equal to 2. Now, here comes the important bit. Here comes the part where this is a little bit different. We are going to need to get rid of that negative 2 on x. And again, this says that we're multiplying x by negative 2, so the opposite of that is dividing by negative 2. But I want you to think about what's about to happen here. When we cancel this side, the negative 2 and the negative 2 cancel, making this positive x. It started as a negative, now is a positive. On this side, we divide 2 by negative 2, now this is negative 1. Started as a positive, ended up as a negative. The signs of our expressions have changed. They've flipped. And the reason why they have flipped is because we have divided both sides by a negative number. In fact, if you divide both sides of an inequality or multiply both sides of an inequality by a negative, it's going to flip the signs of both of those expressions. And because inequalities show weight, the inequality itself is going to flip. So let me go back through that again. We started out with negative 2x and positive 2. We divide the negative 2 off of here in order to cancel it and divide it off here to bring it to the other side. But because this is negative 2, because we're dividing by a negative, both of these signs are going to flip. The signs of each side are going to flip. And because this shows weight, the weight has also flipped. So this started out as this side being bigger and this side being smaller. But when we divide by a negative number on both sides like this, it makes this so that this side is now smaller and this side is now bigger. That is the one big place that inequalities are different in solving them from equations. Equations, you don't have to worry about that because, again, it shows perfect balance. But with inequalities, it does not show that balance, it shows weight, and sometimes that weight can shift. Now, that only happens if you divide both sides by a negative number or multiply both sides by a negative number. And I'll show you one with multiplying both sides by a negative number in a moment here. But let's go ahead and look at this solution on a number line. Okay, so 0 in the middle. Negative numbers on this side, positive numbers on this side. So our solution set is somewhere around negative 1, so I'm going to need to put negative 1 on here. It's about right there. And this says that x is all of the numbers that are smaller than or equal to negative 1. So because I have equal to here, that means that 1 can be included in my solutions. That means I need to use a solid point. Equal to means I use a solid point. And then all of my solutions. X must be smaller than negative 1. So we need to have all the numbers that are smaller than negative 1. Try that again. So it's all of these numbers here. Okay, so now that we've gotten our graph, we can go ahead and go for our interval notation. So my solution set starts here. That is negative infinity, because it just keeps going on and on and on. That's what that arrow shows. And so we read it left to right, starts at negative infinity, ends here at negative 1. So our interval, again, start point and end point. Our start point is negative infinity, and our end point is negative 1. So now we have to decide whether we can put a parenthesis or bracket on each of these numbers. So infinity, we can't ever reach it. It has to get a parenthesis. Every time, infinity will always get a parenthesis. Negative 1, can we be equal to it? Yeah, our solution set says that we can be smaller or equal to 1. So we will use a bracket to show that we can be equal to it. Any questions? This is a perfect time for questions. I know a lot of my students in the past have gotten kind of confused with this whole dividing by a negative thing. So I'm going to allow some time for questions. Okay, I don't see any questions, so I will move on. And I'd like to remind you that if you do come up with any questions, you do not have to wait for me to ask for them. You can ask them at any time. So I promised that I would show one where we are multiplying both sides by a negative. So x divided by negative 3 minus 5 is, let's say, less than, I don't know, 7. Negative 7. Okay. So we're going to add 5 to both sides to get this x value by itself. Cancels there. Have to do the same thing to this side. Now we have x is divided by -3 less than, let's see, -7 plus 5 is -2. Okay, so take note of the signs of both sides right now. This is negative x over 3. This is, or I'm sorry, this is negative x over 3. It's the way you can think about it. And -2. So they're both starting as negatives right now. When I multiply both sides by -3, though, in order to cancel that out, this is now positive x. This is now positive 6. And thus, because we have multiplied both sides by negative, thus changing the signs of both sides, our inequality flips. So now x is greater than 6. So let's go ahead and graph that. Zero in the middle. Okay, 6 is, let's say, about right here. And x is everything larger than that. Now, it doesn't say that x can be equal to, it just says that it can be larger. So we're not going to use a solid dot, we're going to use an open circle. Again, that open circle shows us that, yeah, we're going to start at 6, but we can't actually include it. It just basically starts at 6.0000000000000, and then somewhere there's a 1. And then from there, it's all the things that are larger than 6, because x must be greater than 6. So our line extends that way. So our start point here is at 6. Our end point is at infinity. So when we go to make our interval, again, start point is at 6. End point is at positive infinity. We cannot include 6 because it's not equal to. So we have to use a parenthesis around it, and we can never reach infinity. We can never be equal to infinity. So again, we use a parenthesis around that. Okay, so keep that in mind. If you divide both sides by negative or multiply both sides by negative, you have to flip that inequality to show that the weight has changed, the weight has flipped. All right, so now I want to show you maybe one more thing before we go for today, and that is set builder notation. I mentioned that this thing right here is a set builder. It's kind of true. This doesn't have all of the notation, though. There's some notation that goes along with this to make it a full set builder notation thing, and I'll explain that in a second here. So, when you encounter one of these things, what you're going to see, something like this. Now, this is a very, very simple example of this. They can get much more complicated, but we won't ever get to that in this course. This says, and follow along with me, that we have a set. The curly braces note a set. A set is just a group of numbers described as x, such that x is greater than or equal to 2. So this right here, this x right here, just tells us what kind of variable we're dealing with. And then this is the actual rule for what our numbers can be, what our solutions can be. So you can kind of like cover up this part and this last curly brace and just have x is greater than or equal to 2, and it would make sense. Now, why is the rest of this here? It has to do with higher level algebra. When you get into more complicated algebra, you will find that these actually do have meaning. But again, I'm not going to get into that because it's much more complicated than we need to get to in this class. But it means the same basic principle. We just need to focus on x is greater than or equal to 2. So we can graph that. Our solution starts at 2, so 2 is about right here. We can be equal to 2, so we will use a solid dot. And x is everything bigger than 2. So there's our graph. Our interval notation, we start at 2. We go to infinity. We can be equal to 2, so we will use a bracket around 2. And we cannot be equal to infinity, so we will use a parenthesis around it. And that's it. So set builder notation adds a few extra little details in there, details that we don't need to really be worried about at this point. But it's basically what we've been looking at so far. The reason I want to show it to you, though, is because it gives us opportunities to do more with our sets. So before I move on, are there any questions? Okay, I'm not seeing any, so I'll move on. So again, Set Builder gives us some opportunities for some new things to look at. And that is compound inequalities. Compound inequalities, if we break down that word, compound means more than one thing together. And inequalities, of course, is an inequality. So let me make one of these compound inequalities here. X such that -1 is, let's say, less than x, and x is less than or equal to 4. Okay, once again, you don't really have to worry about this part right here. It's just this part that we, okay, it's just this part that we want to focus on here. You make a better line. This part. So instead of only having one number that x is related to, we have two numbers that it's related to. It's related to -1 and it's related to 4. So what does this look like? Well, again, it's easier to understand what these things are saying if we graph them. So we have to graph both of these numbers. Both of these numbers are locations relating to x. So -1, we'll say, is about right here. And we'll say 4 is maybe right here. So, first look at just this part. -1 is less than x. Okay, there's no equal to there. It's just -1 is less than x. So because there's no equal to between these two, -1 cannot be equal to. It's not part of our solutions. Starts there, but isn't included. Okay, 4. X is less than or equal to 4. Well, because we have equal to between x and 4, we'll use a solid dot to show that we can be equal to. All right, now how about our line? Where does it go? Where's our line for what our solutions can be? So again, we need to break this down. -1 is smaller than x. -1 is less than x. -1 is smaller than x. What that means is that whatever x is, -1 has to be smaller than it, which means, in other words, x is bigger than -1, doesn't it? So, all the numbers bigger than -1 are over here. Well, also this says x is less than or equal to 4. And all the numbers that are less than 4 are over here. So it ends up that we get this line that goes between these 2 points. And there is our graph. Now, our start point is here at -1. Our end point is here at +4. So we have a start point -1, end point +4. We cannot be equal to -1, parenthesis. We can be equal to 4, bracket. Does this make sense? Are there any questions? Okay. One more thing before we leave, and it's another type of these compound inequalities. But this type is going to be sort of interesting. Never mind my roommate back there. So x such that, let's say, -3 is greater than x, and x is greater than 5. Okay, this is going to be kind of weird. So, let's see the weirdness on the graph. So again, we need to mark out where our solutions are. So we have part of our solution is going to be somewhere around -3. Part of our solution is going to be somewhere around 5. So -3 we'll say is like here. And 5 maybe here. All right. So Negative 3 is greater than x. No equal to there, so we need to use an open circle. X is greater than 5. Again, no equal to, so we need to use an open circle. Now this says that negative 3 is greater than x. Well, that means that x is smaller than negative 3. So its line is going to extend into all the numbers that are smaller than negative 3. Again, if negative 3 is bigger than x, then x has to be smaller than negative 3. This also says that x is greater than 5. So it has to be all the numbers that are bigger than 5. So that's what our solution looks like. We don't get a single line. We actually have two lines. Another way of looking at this is that we start at negative infinity, go all the way up to negative 3, then make this jump over all these numbers, land on 5, and keep going into positive infinity. So this solution is saying that we can't be anything between these two. Now, how do we write this in interval? Interval notation is supposed to be a start point and an end point. But we have two lines. Well, the answer here is that we're going to have two intervals, one for each of these lines. So we'll start with this line here, since we always read from left to right. So again, left to right, we start all the way over here in negative infinity. And as we go from negative infinity, we keep going until we get to negative 3. And that's the end of that line. Can't be equal to negative infinity, can't be equal to negative 3. However, we also have this line over here. Again, reading left to right, this starts at 5. Try again with that 5. And goes all the way into positive infinity. We cannot be equal to 5. We cannot be equal to infinity. But there's actually something missing here. We can't just leave it like this, because we need to show that these two lines are actually part of the same solution. And here's how we do that with an operator, new type of operator, called union. It's this really big U symbol. So union is something that we're going to start getting into next time when we talk about how to manipulate sets. So for now, think about union like this. It's like glue. It takes two sets of numbers, so we have one set negative infinity to 3, or negative infinity to negative 3, and another set 5 to positive infinity. And it's gluing them together to make one set, one idea. Okay? So, before we end today, are there any questions? All right, I'm not seeing any questions, so that will do it for us today. So, before we go, I'm not sure when, but I have emailed Mr. Mrzinski to figure this out. Sometime there will be a midterm. I will be turning in grades pretty soon here on Banner, and I'll be sending out grade reports for everybody to let you know how you're doing at this midterm point. But sometime we're also going to have a midterm exam. The reason I'm going to be turning in the grades before the midterm exam is because Lobodin just needs to know how y'all are doing before you start registering for classes for next semester, which, man, let's hope we can meet face to face next semester. All right. So, again, that'll do it for today. I hope you all have a great day, and I will see you on Friday. Goodbye for now.